Hello everyone, today is the 40th day of Leetcode 75 challenge. Let's begin with the 40th question. Question 1161, maximum level sum of a binary tree. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So you are given a root of a binary tree. You are asked to compute the sum of all node values at each level of the tree. Okay, you have to basically compute the sum of all the node values at each level of the tree, starting from the level 1, which is the root. Your task is to find the level that has the maximum sum of node values. Okay, fine. If multiple levels have the same maximum sum, return the smallest level number among them. So basically, if you are given a binary tree, okay, and suppose this is the binary tree. This is level 1, this is level 2, this is level 3, this is level 4. Fine. We have to find which particular level has the maximum sum. Okay, suppose if this level and this level has the same sum, right? So we will return the previous one or the earliest one or this smallest level. Basically, I will return the level 3 in this case. Even if 3 and level 4 has the same sum, I will return level 3. Final output should be an integer representing level number with maximum sum. Fine. The constraints of the problem are the number of nodes in the trees is in the range from 1 to 10 to the power 4, and node value is from negative 10 to the power 5 to positive 10 to the power 5. So the question is pretty straightforward. There is nothing to be think about. We just have to give the maximum sum of the level. That's all. I hope you understood the problem explanation. Now let's move to the next slide. Now let's understand the input-output explanation. So if here you can see, you are given this binary tree and output is 2, which is means that level 2. Okay. So therefore, in this level, we have sum as 1, right? Sum is 1. For this level, we have sum as 2. It's not 2 actually, 7. For this level, we have how much? Minus 1 as the total sum. So out of these three levels, we can see that level 2 has the maximum sum. So our output is 2. Okay. So this is a pretty simple explanation of input output. Now let's move to the next slide. Before going to the further slides, let's understand what is breadth first search. Okay. A BFS. If you already know what is BFS, you can skip this part. Otherwise, please pay attention here. BFS is basically stands for breadth first search. Is a traversal method where we visit all nodes level by level from top to bottom and left to right. This is left to right in general case, or you could go from right to left as per the required question. Right. That's the thing. How it works. Okay, important thing. We start, suppose this is a binary tree. So this is one level, this is another level, level 1, level 2, and level 3. This is clear. Okay, there is nothing much to be understand here. So how we do it? How do we do it? We start from the root node, of course. We use a queue. This is the queue. Okay, we push this particular root node here. Okay, now what we do? We put its children uh, after that. How we do it? We dequeue a node and process it. Suppose we put one here, the root node, we popped it out, and after popping it out, we look for its left and right children's. Left first, then right. And if any question it is required right first and left, then do it that way. Otherwise, the general form is left and right. So if we pop out one, and if we go for the left node, we have 2 here, then we have 3 here. Okay. Now, if you have observed, after doing this, this was level 1, fine. Now this is level 2, correct? Then you popped out 2 also. Then you try to took 4 left and took 5 for this particular node. Fine. Let me extend this. Then you try to popped out 3 also. Then you took 6 and 7. Now, if you have observed, this is level 3. So until and unless the first or the before level is not completely emptied from the queue, you won't be able to access the second no upcoming levels, correct? And every time when we pop one level, we already have been no, filled the queue with the upcoming level of that particular thing or n plus one level, correct? So this way we go level wise for in the particular given tree, and we repeat it until the queue becomes empty. And when we reach at the seventh value or the seventh node in the queue, when it gets empty, that means we have completed traverse our binary tree. Now, why is it efficient? Time complexity is O of n. Each node is visited once. That's why. Space complexity is O of W for each particular traversal, or we could say the maximum width could be O of W, right? Right. If you are storing by chance, if you are storing it in the array, okay, then it will be O of n. But in the queue, the maximum number of nodes at one time could be the maximum width we have in the particular tree. Great for finding the shortest path in unweighted graph or trees. Useful when we want to process nodes level by level. Okay, this is a simple explanation of how breadth first search works. And let me give you one more thing. Suppose you have popped out one from the queue, correct? Then you go for the length of the queue, because when you pop out one, you already have node 2 and 3 under it, right? So the length of the queue becomes 2. So which means we will traverse or we will write a for loop which will go up to 2. So this also isolates each level. Fine. Now, when you will push the child nodes for 2 and 3, the length of the queue will become 4, correct? Then we will take the length of that particular level like this, and again it will isolate, right? So this helps us to traverse in most isolate way and more easier way. Fine. Now, where we use BFS, we used to do when you want to do the level of the traversal, when you want to print or process nodes level by level. Example, print each level of a binary tree on a new line. Okay. When you want to find the minimum depth, BFS stops at the first leaf node, it's fine, correct? Then more efficient than BFS for shallow trees. Find the shortest path from root to leaf node, right? These are the ways where we can use BFS. Okay. Interconnect nodes at same level. BFS easily tracks nodes on the same levels, right? Populate next pointers in a perfect binary tree. So these are the questions you could say, or the logics you could say, where we can use BFS. Suppose in serialization and deserialization of the tree, convert a tree into a flat structure, or doing a zigzag or spiral or traversal variant of level order with direction switching each level. So these are the questions you could say, or the concepts where we use this level order traversal or BFS. BFS is also called as level order traversal because that makes much more sense to hear, right? That's all. I hope you understood this explanation of BFS and how we iterate it. Now let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Let's do it by understanding the goal. So we are given the root of a binary tree, fine. And our task is to find the level in the tree that has the maximum sum of node values. Okay. And each level starts with a root as the level 1, and then its children at level 2, and so on. So we need to compute the total sum of the node values at each level and compare them. So this is the tree. So this is the tree. So if more than one level has the same maximum sum, we return the smallest level number. Okay, these are the things which are clear to us. Okay. Suppose let's go here. If you see this level has, or this level 1 has sum as 1. Level 2 has the sum as 5. Level 3 has the sum as 9 plus 6 is 14, 15, sorry. Minus 5 gives me 10, right? So this level has the sum of 10. And this level has the sum of, 20 minus 10 gives me 10. 10 plus 2 gives me 12, right? So accordingly, the output for this particular binary tree will be level 4, right? Because this has the maximum sum. Okay. By chance, if this minus 10 should have been minus 12, then the sum would have been 10, right? Rather than being 12, right? Then in this case, we would have written level 3 as the output. Fine, because the smallest level is this one. So the brute force way might be to store all the level wise nodes and compute their sum. Okay, but we can do better. So for the brute force, what comes to our mind is that we will use BFS. Okay, we will take a 2D array or 2D list and 1D list. Okay, 1D list will keep on getting updated at each level. So what we can do is that at each level we could we will store the values of each level in the 1D list, and when this traversal of the particular level is done, okay, then we will store this 1D list into our 2D list. So it will become like this: level 1 list, level 2 list, level 3 list, right? It will become 2D list, okay, in total. And then what we could do, we could traverse each row, compute the sum, and return which row number has the maximum sum, right? This could be done. This is the one way of doing. But in this case, what would happen is that your traversal is correct, but you are using an extra space, right, for storing the values. And that too, you are using it two times. First for the 1D array at every iteration, okay, 1D array, and second for the 2D array, okay. And after that, you are iterating one more time, which will take again O of n square, because since it's an 2D array, okay. So the time complexity will be very much, right, or it won't be much as efficient as we want, okay. So what we can do is that we aim to traverse a tree level by level, okay, and calculate each level sum on the fly using Q. Q because we will be using a BFS, right? That's why we will be using Q, but we won't be storing any value into our list as we were storing in this 1D array. Fine. Nor we will store that 1D or anything in the 2D array. So we will try to remove this space complexity from our solution. Now let's visualize the process. We perform a level order traversal or breadth first search, which is common to our knowledge, using a queue to process nodes level by level. That is understandable, right? So let's take a tree. Okay, let this be the tree. Okay, we will perform level order traversal. Okay, and at each level, we will calculate the sum of all nodes values present at at that level. Okay, we will try to calculate the sum present at each level, right? How we will do that? Everyone knows how BFS work. Okay, so when suppose this is the queue, right? We have pushed. What we will do? We will push the value in the queue initially, and then when we will pop this value, we will have a current sum value. Fine, the value which we will pop. Okay, this is the popped value. Let this be the pop value. Fine. So this is done. So what happens is this is that now when we pop this value, we have this. Okay, and since we have to find the maximum, right? So what we will do? We will also try to take a variable max. Okay, and we will initialize it with the most negative value that could happen, right? Negative infinity. So when the sum is calculated for this particular level, this is the current sum, right? So we will compare it with the max. Okay. Now, since max is negative already, so one will be the maximum for it, right? Since it is negative, so this will be the maximum for it, right? So when we pop this value, and when the iteration is done for this, so we will have 2 and 3 in our queue, because the child of one are 2 and 3, right? So when we will, and this current sum will get updated to 0 again. Fine. That could be done, because at each level we have to count the fresh sum. Okay. So what happens now? We have 2, right? So we will add 2 into our current sum. So our current sum will become 2. Okay. Then we will check for the left and right nodes for 2, which is 6 and 5 respectively. So we'll put it there. Okay. And after that, we will pop this value. Correct. We will initially only pop this value, and then we'll come to the 3. We will pop this value. We will take it and we will add these 3 to our current sum. So our current sum becomes 5, right? And what we will do, we will take its children's. So 3 children is this. This is 6 minus 6. Okay. So we are currently in this level and storing the values of the next level. Fine. So this is 5. And if we come after this after this level is done, we will come out of the loop, right? And we will check max value, right? Now max was 1, so it becomes 5. Great. And when we update the max, whenever we will update the max, we will store the level also. So this is, in this case, this is level 2. Fine. This is the things we will keep in mind. Okay. Then we went up. Again, we will check. Okay, now we have 6, and current sum has become 0 already, because this is a fresh new level. So this will become 6. Great. Then we put the values of 6 children, which is 3 in this case only. 3. Okay. Then this is popped. Then we have 5. We will add 5. Okay. This popped. Since it doesn't have any child, we will ignore that part. Then we will come to 6 minus 6. We have popped this value. Children of 6 are 1 and 0, right? And total sum comes out to be 6 get cancelled. We have 5, right? So we come back here. We will check, okay, since max is already 5, so we don't update anything. And level also, we won't update anything, right? This way, what happens is that suppose this level is also 5 and this level is also 5, right? If I have not taken the consideration that the current sum has to be strictly greater than the max. Okay, not equal to. If I have given equal to, then what would happen is that we'll get the latest level, and which is wrong because we want the smallest level when we have the same sums. Okay, that's why we'll keep it as strictly greater. Okay, then this is done. So our current sum becomes zero here, and we have three. We pop three. We put it here. Since three doesn't have any child, we will ignore it, and we'll go ahead. We'll pop one. We will add it. It also does not have any child. We'll pop 0. We'll add it. So our sum becomes 4, right? And sum 4 is smaller than the max. So we won't update the levels and our iteration will get completed after that, right? So after that, if you can see, we have 5 in our answer, max, and level is 2. And according to our understanding and the question, we got the correct level, which is this, right? It should be the answer. And this way we have implemented our intuition, or we have realized the process that how we're going to solve this particular question, right? Now how we can simulate this, right? We will initialize a queue with a root node, okay, and set variables for max sum and answer level, right? These are the variables which will be needed: maximum sum, answer level, and queue will be initialized with the root node, right? While the queue is not empty, what we will do, we will determine how many nodes are there at the current level, and this is done by using length of queue. Length of queue basically tells us that, suppose this is the queue, right? 3, 4, 5 is the value in it. This length of queue will tell me that, okay, suppose these are the parents, okay, of any level X, okay. So if I take the length of this particular queue, it will be 3. So at level uh, X, total number of nodes are 3. Okay, this what this means when we take out the length queue. So when we iterate and put the child of these particular nodes, okay, let it be C with the child of these particular 3 nodes, what happens? Since we have the length as 3, right, even though the queue length has decreased and increased both simultaneously, it won't affect that particular thing. It says that at level 3, the length is 3, or at level X, the length is 3. And when this particular all the nodes gets out, length also becomes 0 because we keep on doing length minus minus, right? And that way, when we come back to the process of taking the length again, we will get our length as 4. So this is the way this how it works, and it isolates every level. And this is what we are doing here at 3.2.1 point number. And we initialize a variable to store the sum of the current level. And this sum variable will be stored under the for loop of the size of the length, because sum has to be get updated every time at each level. How we're going to do this? We will dequeue a node, and we will be using dequeue in our case, fine. So that you can pop from front also. If in Python, dequeue helps in pushing and popping from front and back. Okay, that's why we will use dequeue in our case. NQ, its left child, it exists. NQ, its right child, it exists. This is the concept of breadth first search traversal, or the level order traversal. That's all. And after the loop is done, we will compare the current sum with the maximum sum. Okay, when the iteration of the particular level is done, then we will consider, or we will check in this particular level, right? If greater, update the max sum, we store the current level number as the answer. Otherwise, we move to the next level and update the level variable. That's all. And what we figure out from this particular question is that the key insight is to process the tree level by level and compute sum as we go. Instead of using BFS, making the question much complex, we will use BFS, which makes much more sense on the level of the traversal, right? By comparing each level sum in real time, we avoid need for extra space or seconds passes. If you remember, since we calculated the level or the sum in each level and updated the current sum in each level, we didn't need any 1D array or 2D array or any kind of list, and we didn't need any kind of iteration after the complete iteration of the tree is done, right? So we have reduced a lot of time complexity and space complexity because of it. And we ensure that if multiple levels have the same sum, the smallest level number is returned. This is done by using strictly increasing concept or strictly increasing condition. The current sum is strictly greater than max. This approach is efficient and elegant, requiring only single BFS traversal and constant extra space required. Fine. So I hope you understood the intuition. Now let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach how we're gonna solve it. First and foremost condition is root is none, we return zero since there is no label to evaluate, right? If the tree is only not present, tree is itself null or none, the label has to be zero, right? Because there is nothing. Otherwise, we initialize a variable sum to store the maximum sum seen so far. We'll declare a sum variable and initialize is negative infinity because this will store our final answer or the maximum value. Fine. Till now. Okay. A queue, which is basically a DQ, and add the root node to it. This help us to perform level order traversal. This is the concept of level order traversal. A variable level set to 1 to track the current level number. We will store a level variable which will be stored to 1 because root node level is considered as to be 1, not 0. Fine. A variable answers to store the level number with the maximum sum found so far. And also a variable answer which will store the final output of the level. Okay. Whenever we will get a maximum sum compared to this particular sum, we will update the level also in our answer and the sum also. Why? Because we want to visit every level and calculate the sum of values at the level. The queue let us process nodes level by level. Now in step 2, we will perform the level order traversal, which is BFS. We begin a level queue like this. While queue is not empty, we will take the size of the current queue, right? And after that, we will go for size, right? While size is not equals to 0. Or while I is not equal to size. You could go like this, 0 to size. So these are particular nested stuff. This comes under this and this comes under this, right? We determine the number of nodes at each level using this. Okay, if you remember, I explained it earlier in this particular case. This one, right? After that, this helps us to isolate the process all nodes that belongs to the current level. This is the concept which we discussed earlier. Now at step 3, we process each level and compute the sum. Okay, this is the main concept. We initialize current variable to 0. Current. This will store the current level sum. Okay, at each level, and for each node in the current level, for range this to of size, right? This we pop left because this is the queue. Pop left because we are using BQ, right? As I explained, we could pop and push from front and back, right? This could be done. So therefore, we pop left. We do it this way. Okay, from the queue, add it to the current sum, and if the node has the left child, we add it to the queue. If it has the right child, we add it to the queue. Fine, that's all. There's nothing else. And why we do this? Because we gather all nodes for the next level while simultaneously summing values at the current node. If you can see, we're summing the values at the current level, right? Without storing anything. And we're pushing the child nodes to the queue. Right? And after the process is done, all the nodes at the current level, we will check if current is greater than the sum. Okay, we update the sum and set the answer to the level. This is the final check which we do after each level. Okay, we then increment the level to move to the next level in the loop iteration. That's the common thing. Now in step 4, it's a final output. After the loop ends or the traverse of the complete tree is done, right? We return the answer which consists of the maximum sum of the nodes. That's all. This is all about the approach. I hope you understood the approach. Now let's go to the next slide. The code is the exact copy of the approach we discussed. Let's understand it line by line. If you could see, if root is none, return 0. This is the base case. After that, if it is not true, what we do? Sum, which stores the maximum sum so far, we initialize it negative float value. Okay. We initialize the queue, initialize the label, we append the value row of root node into the queue, and we initialize answer. This stores the final level. This updates while we iterate for each level, right? If you could see, we have in the while loop, if you could see, we have taken the size of the current level. We have initialized current to 0. This stores the current sum of the current level. Now we iterate, right? For this range, we pop the value from the left, we add it to the current, we check left and right exist, we append it to the queue. And after this for loop iteration is done, we check if the current sum is greater than the sum we got previously. If it is, we store the level into the answer, current into the sum. Okay. And after that, we increase the level. And then we come back to this queue again and we do the same thing again and again until the completely queue is empty and we return the answer at the end. Now the time complexity for this particular problem is O of n because it is a one pass solution, and space complexity is O of w because since it is not considered because it is not considered usually, but in this case since we are using queue in BFS, since we use queue data structure or the concept of queue, and here we are using DQ data structure, it store maximum number of the number of nodes which is stored is maximum of the particular level, right? Suppose if level 3 has 10 nodes in that particular level, which is not possible, but just take it as an example, it has the maximum node, then queue will have that particular there's those 10 nodes in it once, right? And other other levels might have eight nodes, 3 nodes, or 4 nodes, right? So maximum number of nodes stored in one iteration was 10. So therefore, the maximum space complexity taken by it will be O of W, or the width, or the breadth, right? So this is the code explanation. I hope you understood it. Now let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. So this is the example which I have taken, and this here I have already brought the code here for understanding. Now let me draw the tree first. Okay, let's begin with the dry run. The first thing we check is if the root is none. So it is not none, right? So we don't return anything. So in the sum variable, let me write it here. In the sum variable, what we do, we have some negative value in it, right? Let it be minus infinity. Okay, and we have the level variable then, which is one, and we have the root. Let me draw the queue here. It will be much better to look at. Then we have answer variable and slash to 0. So label is done, this is done, and in the queue we initially we have appended one. Fine, this is done, this is done. While queue is not empty, right? So we have the current variable here, right? Let me write it here, current. It will show the current sum. And anything else do we have? We have no, nothing. Okay, let's begin. So this is done. Now while queue is not empty here, in size variable we will store one. One is the length because the length of the queue is one, right? So this iteration will go till one. Fine. And current is 0. We pop the node here, which is 1. Let me write. We popped it, we stored it in the node variable, and then we added this node val to our current, which becomes 1 then. Okay. We check for the left. We have the left variable as 7. We push it into the queue. And in the right node also. So we'll push that also into the queue. Great. This is done. Okay. Yeah. Then we check if the current sum, which is 1, is greater than the maximum sum or not, or the sum. So since it is minus infinity and 1 is greater than minus infinity, we will replace it with 1. Then we move ahead, and answer is also updated to the level, right? So answer becomes 1, and level increased to 2 after that. Great. Now in the queue we have 7 and 0. So we take the length of this particular queue, which is 2. Then current is initialized to 0 again. Then we will go to the range. This one. We'll pop the value. It is 7, right? Add it to the current, which is 7 now. Okay. Size becomes 1. We will check if we have left and right nodes. We have. So we'll push it into the queue, which is 7 and minus 8. Okay. After that, this is done, right? So this is popped. Now current sum is 7, right? So we pop 0 now. So we have node 0, current sum still remains 0 after adding 0, and size becomes 0. This is fine. Then for the 0, we don't have any left, so we have only have the right node. So this is true in our 0's case, so we'll add it here. And after that, since size becomes 0, so this particular loop iteration is done. We come out, we check that if current sum is greater than the maximum sum so far. So it is. So it becomes 7. The level is, the answer also gets updated to level, which becomes 2 then. Okay. Everything is done, and level increases to 3. Great. Now we came back again, same process. Now node has nothing. So we pop 7. 7 is here. Great. Then the current sum becomes 7. Size was how much? 3, right? Let it be 3. So it also reduces to 2 then. Fine. We check if 7 has left and right. It doesn't have anything, right? Okay. We pop minus 8 now. We check we add it to the current sum. So it becomes minus 1. Size also reduced to 1. Now we check does it have left and right? It do have. So we will add minus 8 and 2. Okay. Then we'll go ahead. We'll pop 9. So node has the 9 value. We add it to the queue current variable. So 9 plus minus 1 gives me what? 8, right? Size becomes 0. We check whether it has left and right. So it does not. This case becomes false, right? The complete iteration is done for this particular level. We come out. We check if the current sum is it greater than the sum so far, maximum sum so far. Yes, it is. So it becomes updated to 8. Answer also increased to 3, and the level also increased to 4. Fine, and everything becomes 0. Now in the queue, since queue is not empty, we pop minus 8. We add it to the current sum. Since size was 2, right? So it becomes 1. Great. Again we go. Since it does not have any left and right, we will ignore that, right? Again we will pop 2, add it to the current sum. So sum becomes minus 6. Size becomes 0. So size is done, and it does not have any left and right. So this particular thing is done, right? For loop is done. Now we check if minus 6 is greater than sum. It is not. So this won't be get so this won't get affected. Level will increase to 5, but since when we go back to the while loop, we will check. So we will see that queue is completely empty. So nothing happens in this case. So we come out and we return the answer, and answer is 3, right? If you look at the tree, sum for this level is 1. Okay, sum for this particular level is 7. Sum for this particular level is 9 plus 7 gives me 16. 16 minus 8 gives me 8, right? Sum for this level is minus 6. So according to our understanding and the question explanations, the output should be 3, right? Level 3. So which is our output here. So I hope you understood the dry run. If you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach and the code, and also the knowledge of BFS. After that, do a dry run by yourself on 2, 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Now let's move to the next slide. Now, since you're familiar with the problem and the solution, let's move to the lead code and code the solution. If root is none, we used to return 0, correct? Then we will declare a variable sum, where we will store the negative infinity value. We will declare the queue. We will append the root node to the queue. Then we will declare an answer variable, which will store the maximum level sum. Okay, which will store the level which has the maximum sum. While queue is not empty, we will take the size of the current level of the queue. If we initialize the current sum to 0 or the current level sum to 0 for range of size, we will take the node by doing queue dot pop left. In current, we will add the current sum node dot val. If node dot left exists, queue dot append node left. If node dot right exists, queue dot append node right. And after that, we come out of this loop. We will check if the current is greater than the maximum or not, the current sum till now or not. If it is, answer is updated to the level, current level. Sum is also updated to current, and this is the default level will increase in each iteration. Fine. And after that, we will just return the answer. Let's try submitting the sample test cases. Okay, now finally submit the solution. We have successfully submitted our solution. Now, code of the problem is available in my GitHub repository. You can find the link in the description. Thank you, everyone.